So I have first calculated the element stiffness matrix in the local coordinate system for element number 4. The local coordinate system was this. And then I have transformed this element stiffness in the local coordinate to an element stiffness in the global coordinate for element number 4. And I have said that we will do that for each and every element. So for each and every element, we will connect the, the degrees of freedom at its nodes to the forces at its nodes in the global coordinate system. However, when you look at node 4, it is part of a whole structure. So when you try to apply a force at node 4 in the x or y directions, then the motion of node 4 depends on the stiffnesses of element 5, element 4, and element 6. When you try to move this node, node 2, it is affected by stiffnesses of this, of this, of this, and of this. So we have to somehow, the connectivity information that we have between the nodes, we have to somehow transfer that into the finite element equations, and that's the procedure of assembling the element stiffness matrix. After you have got the element stiffness matrices in the global coordinate system, you have to assemble them to get a global stiffness matrix from the element stiffness matrices. How big will the global stiffness matrix be? The global stiffness matrix will, if there are n number of nodes in the whole system, in our case nn is equal to 5, and if the number of degrees of freedom per node is equal to 2 in our case, then our global stiffness matrix will be 10 cross 10, just like our elemental stiffness matrices were 4 cross 4, because the number of nodes in an element were 2. Okay, so the whole structure is just like a super element. It's composed of many elements. I first find the stiffnesses of each element and then I assemble them to get the stiffness of the super element. Okay, so to do that, we have to know this connectivity information. We have to know which nodes are connected to which elements, which will immediately tell me which degrees of freedom are connected to which element. So the way that works is this. We have already seen this transformation, that the element stiffness matrix in the global coordinate system is related to the transformation matrix to the element stiffness matrix in the local coordinate system. So this is a 4 cross 4 matrix, and this is also a 4 cross 4 matrix. Now let us imagine that we know the connectivity. So this is node number 2, global node number 2. This is global node number 4 connected to local node number associated with local node number 1, and this is associated with local node number 4. Once we know the global node numbers, immediately we know the global degree of freedom numbers. These are 3 and 4 and 7 and 8 for element number 4. So I do this kind of associativity. The reds are the global degree of freedom numbers. So they are, the first one is for local number 1. This is K11, and this is associated with global degree of freedom number 3. Similarly, local 2 is associated with global 4, and I do that in along the rows. 7 is associated with 3, 4 is associated with 8. I do that along the I do that along the columns, and then I do that along the rows as well. Remember, this whole thing is a 4 cross 4 matrix, giving a 4 cross 4 matrix. The reds are the global node degree of freedom numbers, and the blacks are the local degree of freedom numbers. Now, once you have done this, you can make something called a destination array, and the destination array is has two arguments. E is the element number, which goes from 1 to any being the total element number of elements in the mesh. So any in our case is 7. And D goes from n node, which is the number of nodes per element, our case 2, to the number of degrees of freedom per node, which in our case is also 2. So we will have in our case a destination array which has which is 7 cross 4. We'll have a 7 cross 4 destination array which will tell us uh, which element which degree of freedom goes globally to which number in the global system of things. Because when we assemble the global stiffness matrix, which we call K, this is the ordering that we are going to use. We are going to use capital U1 to capital U10. These are the 10 degrees of freedom associated with the 5 nodes, and similarly the 10 external forces associated with the 5 nodes with 2 degrees of freedom per every node. So the global stiffness matrix connects the entire set of 10 degrees of freedom to the entire set of 10 force components. So this is going to be a 10 cross 10 matrix, and this is a 10 cross 1 vector. This is a 10 cross 1 vector. So we are now going to form this 10 cross 10 matrix, and to do that we will have to create this destination array. So the destination for 1, for example, so means that destination of element number 4, degree of local degree of freedom 1. So destination of 4 1 is 3. So go back, destination of element number 4, local degree of freedom number 1 is global degree of freedom 3. Similarly, destination for let's say 4, destination for 4 means element number 4, degree local degree of freedom 4, which is this, is going to 8. So the destination array for E1 to 4 will be 3 3 4 7 8. Okay, so this is how the destination array has to be stored, and it has to be stored for each and every element. We can try it out for another element. Let's say let's try it out for element 5. So destination 5 1 will be 9, 5 2 will be 10, 5 3 will be 7, and 5 4 will be 8. So check this out. For each and every element you need the whole destination array, and once you have that, then you can decide where your local stiffness matrix, which is this quantity, where its local stiffness matrix is going to go. So once you have this destination array chalked out, the assembly can happen in a very standardized manner if you can code it properly. So let us take one example for the local stiffness element of element number 4, the local stiffness element 2 2. So these are local node numbers. So we have to look at destination of element number 4's degree of freedom 2, which we know is 4. We again have to look for the same thing here. This also will be 4. Therefore, this has to go to global 4 4, and it has to be added to whatever was existing in global 4 4 before, because the global degree of freedom 4, which is here, is going to have contributions from element 2 and element 3 before it has contributions from element 4. So we have to keep the contributions from 2 and 3 when we add 4. Similarly, it will have contributions from 7 after that. So we will have to then keep adding these contributions. So when we assemble 7, we will have contributions from 2, 3, and 4 already at this degree of freedom. And that is ensured by the fact that we add this local contribution to whatever was existing here. Similarly, if we take element 4's local 3, 1 component, then destination 4, 3 is equal to 7. Destination 4, 1 is equal to 3. So this will now go to K7, 3. Now, you might have noticed that the local stiffness matrix is symmetric. There's a physical reason for why it's symmetric, but at the moment, you might have seen that it is symmetric, and the global will also be symmetric. The global will also be symmetric. So this 7, 3 will be the same as 3, 7. So sometimes we just assemble only the upper part of it, the part above the diagonal, and do not store the parts below the diagonal. So you can put this in 7, 3, or you can equivalently put this in 3, 7. Really doesn't matter, because your stiffness matrix is finally symmetric. So this is how the assembly process goes. Let us now look at the destination arrays for our mesh and assemble things for, let's say, element numbers 1 and 2. So the assembly will go one by one. First element number 1 will be assembled, 2 will be assembled, 3, and so on. So let's just do it for 1 and 2. So when you do it for 1, so at 1, local degree of freedom 1 and 2 are associated with global degrees of freedom 1 and 2. This is node number 5. So global degrees of freedom 3 and 4 are associated with local degrees of freedom 3 and 4 are associated with global degrees of freedom 9 and 10. So this is the destination array that you have, 1, 2, 9, 10. And then for element number 2, this is, let's say, local 1, and this is local 2. Then this is associated with 3 and 4, and this is associated again with 9 and 10. So the destinations are 3, 4, 9, 10. If you had called this as the local node 1 and this as the local node 2, then it would have been 9, 10, 3, 4. And in that case, your XL axis would have been like this, YL would have been like this. We have taken this to be 1 and this to be 2, so our XL is pointing in this direction. Remember, when XL points in this direction, it points always from local node 1 to local node 2, and then the equilibrium equations will be affected by the choice of your XL direction. So whether you take 5 as 1 and 2 as 2, or 2 as 1 and 5 as 2 will make some difference, and this destination array will also be different. So this is for element numbers 1 and 2. Now let us see what the assembly would be like. So first we assemble element number 1, and then we assemble element number 2, but between 1 and 2 we have this degree of freedom common. This node is common. So the degrees of freedom 9 and 10 are common between 1 and 2. So at 9 and 10, both of these elements will contribute. So when you look at the stiffness, local contributions will come here. Once 1, 1 for 1 will come here, because this is 1, 1. 2, 2 will 1, 2 will come here. 2, 2 will come here. This is also 2, 2. And then 3, 3 will go to 9, 9, and 4, 4 will go to 10, 10. Okay, you can fill up only the upper triangular part, and the lower triangular part will be the same, right? this is how it will be filled up. So uh, my degrees of freedom are 1, 2, 3, 4, and they go to 1, 2, 9, 10. So 1, 1 goes to 1, 1, 2, 2 goes to 2, 2, 3, 3 goes to 9, 9, 4, 4 goes to 10, 10, 4, 3 goes to 9, 10, or 10, 9, 3, 2 goes to 9, 2, or 2, 9, 1, 2 goes to 1, 2. That's how you assemble this for element number 1. Then we come to element number 2. In element number 2, uh, first degree of freedom is 2. That's how we have written the connectivity. So first degree of freedom is 2. So 1, 1 goes to 3, 3, 2, 2 goes to 4, 4. So 1, 1, 1, 1 for 2 goes to 3, 3, and 1, 2, 2 for 2 goes to 4, 4. Okay. Then 3, 3 goes to 9, 9, but 9, 9 already has a contribution from element number 1. So you will have things adding up there. So this is the 3, 3 contribution from element number 1, and this is the 3, 3 contribution from element number 2. 4, 4 also will have contributions from both element number 1 and element number 2, and that's also shown here. You can carry this out and you can complete the assembly for all 7 elements in the mesh, and then you will have a full stiffness matrix, that full global stiffness matrix, that will look like this. So this is, as I said, it has several properties that are guaranteed by the kind of elasticity problems that we are solving. The first property, as I said, is uh, it's diagonal. So the part above this diagonal and below the diagonal are the same. It's symmetric. It is also diagonally dominant. Um, that means the diagonal terms here are significantly greater than the off diagonal terms. Uh, right now, it looks as if it covers, it's a 10 cross 10 matrix, and that is what is expected because there are 5 nodes and 2 degrees of freedom per node, so we'll have 10 cross 10 matrix. It seems to have, it seems to be spread all over the 10 cross 10 space, though there are vacant spaces here. These vacant spaces are zeros. There has been no contribution there, and this is generally another hallmark of stiffness matrices. They are what is known as sparse. So there are a lot of spaces which are zero, and this becomes very important when you have very large structures and you have to store very large stiffness matrices, and then the sparsity can be taken advantage of, and we can store only the upper triangular, only the non-zero components in the upper triangular part, and not worry about the zero components. So these sparse functions are available in MATLAB. It's also available. It also makes the computations faster. Uh, Keeping that aside, uh, let us see what governs the filling of this uh, global stiffness matrix. Now, what you can see here is that let's look at row 1. Row 1 has contributions from degree of freedom 1, which is here. Okay, and this is connected to node number 5 through element 1, and it's connected to node number 2 with element 3. So this has global degrees of freedom 3, 4. This is global degrees of freedom 9, 10. So when you assemble element number 1, you will make contributions to 1, 1, 2, 2, 9, 9, and 10, 10. So your matrix will fill up, your first column will fill up 1, 1, 1, 2, 1, 9, 1, 10, and these are that 1, 9 and 1, 10 here. When you assemble for element 3, it will fill up 1, 1, 1, 2, 1, 3, and 1, 4 in the first row. So those contributions are 1, 3 and 1, 4 here. 1, 1 and 1, 2 has contributions both from elements 1 and 3. Okay, so if this were not connected to node number 1, then this matrix would have gone only up to here, because it's connected to a maximum degree of freedom number 4. Since it's also connected to node number 5, which has degrees of freedom 9 and 10, it's extending all the way up to here, and so 1 is connected to 10. That makes the matrix, the non-zero part of the matrix, wider, and we call it that it increases the bandwidth of the matrix. Now, if I could do a cleverer numbering of the nodes, so that I check out the maximum difference between the numbers of connected elements. So maximum between 1 and 3 is 4, and the maximum between 1 and 5 is 10. If I can reduce this difference between the maximum, then I can actually narrow the bandwidth down, and that's what I'm going to show for this new numbering that I have changed the numbering to 1, 2, 3, 4, 5. And when we do that, now 1 is maximum connected to degrees of freedom 4 and 5, degrees of freedom 5 and 6 here. Here it's connected to 3 and 4. So the maximum is 1, 6. So 1 now goes up to 6, and this has reduced the bandwidth. This is called the half bandwidth, and the rest of it is symmetric, as we know. So the half bandwidth has been reduced considerably from this case, and this becomes very important when you deal with very large structures. You have to reduce the bandwidth, and this is not really a finite element problem. This is a problem that borrows, there are standard algorithms that borrow from graph theory, and these are available. So you can do an automatic minimization of bandwidth by optimizing the node number. So initially you do an arbitrary node numbering, then you pass it through an optimizing code, and that changes the node numbering, changes the element connectivities, and gives you back a better node numbering that gives you a thinner matrix about the diagonal. So this is all about assembling. And finally, you have to put in the boundary conditions and the external forces. In this case, in our case, okay, we are going back to the previous original numbering that we did. This I just showed to demonstrate to you that you can cleverly number the nodes and reduce the bandwidth, but we are going to go back to this numbering. And in this numbering, we had only forces applied at the nodes. No forces were present at any of the nodes except at node 5, where the force in the x direction is minus F1 and the y direction is F2. So that's the only force that we have. So the external force vector is very easy to assemble here. So the external force vector, capital F, looks like this. And the assembled global stiffness matrix is this. The global degrees of freedom run from 1 to 10. So you have this big matrix equation KU equal to F, which is the global stiffness connecting the global degrees of freedom to the global force vectors, or we sometimes call it the RHS also. So in our case, there are 10 global degrees of freedom. There are 10 global forces, external loads, of which 8 are 0 and 9 and 10 are minus F1 and F2. So that's what we have. And now you might think that you can just do inverse of K into F and you will get U. but that's not going to be the case because K is going to be a singular matrix. So let's see why and let's see how we can deal with it.